Okay, let's have a look at atomic theory development, or the development of the model of the atom and therefore the model of matter. So, most societies have an idea of what matter is or a model of what matter is, but we take our initial view from the Greek period, about 2,000 years ago, with a philosopher named Democritus who said that matter could be continuously divided until we reach an indivisible point, or an indestructible point of particles, which he called atomos. Now he was very forward-thinking. A lot of his contemporaries said no, that's not the case, and it took roughly 2,000 years for this idea to be re-looked at. And it came about by the way of a scientist called Dalton. In the early 1800s, he performed experiments and came up with three principles. Firstly, that each element, so they looked at the process of elements, is composed of small indestructible particles called atoms. So he drew on what Democritus and Democritus's contemporaries said to give us that. He used empirical evidence or performed experiments to do this. He also said that, or proposed that all atoms of the same element have the same mass and the same properties that distinguish them from other elements. So it was that forerunner to developing the periodic table and looking at elements as unique substances. Finally, he also said that atoms can combine in simple whole number ratios, and he did this through his work with gases. Now, it took a further 100 years for scientist by the name of Thomson to make the discovery of the electron. And he proposed that the electron had a charge, and he designated this as a negative charge. He also said that electrons were very small. So from this model, or from this data, from this proposal about the electron, he also proposed that there must be a positive balancing charge because atoms have an overall neutral charge. So he proposed what was called the Plum pudding model. And in that model, there was a sphere of positive charge, and interspersed within that solid sphere were our electrons, were our negatively charged particles. Now, one of the people that worked underneath Thomson was another scientist called Rutherford, and he conducted an experiment to try and confirm what Thomson had said about the Plum pudding model. So he set it up in an experiment where he had a source of alpha particles, or a type of radiation. He had a very, very thin piece of gold, and he had a detector screen at the back. And based on Thomson's model, he said that all the particles, all the alpha particles, being very small, will travel right through to the detector, and they will all hit in the same spot. However, what he found was that this wasn't the case. He found that most, but not all, alpha particles travelled through. His detector, out at some of the fringes, also found alpha particles out here. And this was a very unexpected result. Because if we look at the Plum pudding model, we have our alpha particles travelling through. There's not much in there that they can hit or be deflected by. So he reasoned that they should travel right through to the deflector screen. So he had to rethink what he thought, because something within our atoms of gold were deflecting those particles, either charge or mass or both. And this is what he came up with for his model. He said that most of the mass of an atom and all of its positive charge must be contained within a small, dense area. And that if we get an alpha particle coming along, or most of the alpha particles that come along will not be deflected. But some of those alpha particles will either be deflected by this positive charge, or by the mass, they'll bounce off the mass that's in the centre of that particle. He called this small core the nucleus, and we know it as the nucleus these days. He also said that most of the volume of the atom is empty, and that electrons travel through this. So the evidence that most of the alpha particles travel through indicates that most of this space in the nucleus is also empty. And finally, he said there are as many negative charges, which we know were electrons, as the positive charges, and he called those protons. So this gave us the idea, once again following on from Thomson, that an atom is electrically neutral unless we remove or add electrons to it. Now there have been some further developments within the last century. We're only going to look at those that involve the three fundamental particles. So from these developments, we now have a nucleus for our modern model of the atom. And the nucleus contains protons, which are positively charged. They have relatively high mass, and they determine what element we have. So the number of protons determines the elements. Within the nucleus, we also have neutrons. They are neutrally charged. They have a high mass, and as we'll look at later, they determine what our isotopes are. So isotopes are the same element, but with different mass. And finally, we have electrons, which exist in a cloud around the nucleus. They have a negative charge. They're a very low mass, but they determine the properties, and they also determine the size of the